Hello, my name is Assam Tashinov, and this is my Torchbearer project that I am doing with Will Stroll. In our Torchbearer project, we'll be uploading YouTube videos in which we analyze mathematical problems, English books, history. It's basically just an educational YouTube channel, which we hope will help others in the future. Will not be in this video because he will more than likely not be doing the math subject. But today I will be doing exercise 1A from the IB higher level the textbook for analysis and approaches. So let's go ahead and get started. Now, basically, this whole unit is just about series, sequences, and proofs. First exercise is simple arithmetic. We're given a couple of sequences and we just need to find the next three terms and the general term for UN. 1A gives us these couple of numbers, 3, 4.5, 6, and 7.5. Now off the bat, we can recognize that U is going to be our U1 term. And our difference here, we can count, just simple mathematical plus 1.5 each time. Whoops, let me mark that out. Yep, plus 1.5, which is going to be our difference. Now, if you remember back from earlier on in the textbook, sequences are given through this equation. UN is going to be equal to U1 plus D n minus 1. So let's go ahead and first just write the series or the sequence since we know what that is. So UN is going to be equal to U1, which is 3, plus D, and our D is our difference, so 1.5, n minus 1. Let me erase some of this. All right. So here is solution to that. But remember, it's also asking for the next three terms, so you just gotta add 1.5 each time. So next we get 9, then 10, and 12, and boom. That's 1A done. Scroll down and start 1B. Now 1B, this time we're decreasing. When you look at these sequences, you should recognize that it's either increasing or decreasing. Here we're actually going to be decreasing. So we know our difference is going to end up being negative. Let's first recognize our U1, and that's going to end up being 17. Let's look at the difference here. The difference is just going to be simple minus 3 each time. So this time, let's just do our next three terms first, which is going to end up being 5, then 2, and then negative 1. Simple like that. And let's go ahead and write out our sequence here. So UN is equal to U1, which is 17. And then since our difference is actually negative 3, this is no longer going to be, plus D. It's going to be minus D. And it's 3 and minus 1. And there's our solution. Okay, 1C is next. Our sequence here is 3, 9, 27, 81, dot, dot, dot. Okay, so when I'm looking at this, I see there's no simple, addition here that'll get me from each one. We have plus 6, and then we have, what's that, like plus, like 18, blah, blah, or, yeah, 18, all of that. So obviously there's no simple addition here, but you can still recognize that U1 is going to be equal to 3. And in cases like this, it's pretty easy to see that the next number is just going to be the first number and then squared, cubed. But when it's not as simple like that, we can actually find the ratio here. And we can do that by doing U2 divided by U1, which in this case is going to be 9 divided by 3. And that's equal to 3. And then if you try with 27 divided by 9, look at that. We have 3 again. So this tells us that it's going to be 3 to the power of something. So from here we can write UN is going to be equal to 3 And then since there's no extra addition going on, we just know it's going to be un is equal to 3 to the n, just like that. And then for the next three terms, you'll more than likely need a calculator for this, but I have it down right here, and it's just going to be 243, which is 3 to the power of 5, and 729, and oh no, I'm running out of space. Right here, we have 2187. That is our answer. Let me erase a couple of this. Just getting that out the way. Right, next one. 1D. 1D, it starts to get a bit more trickier here. We're now given fractions instead of, whole numbers. So let's write these down. Now, in cases like this, there isn't going to be any, simple common ratio you can find. It's not going to be anything like that. So we just have to recognize patterns here. What we see going on is on the numerator is adding 3 each time. Plus 3, plus 3, plus 3. And good thing for us, on the denominator, it's also doing the exact same thing. Plus 3, plus 3, plus 3. So we can already easily find out the next three terms by just doing plus 3 on each of these. So we have 13 divided by 6, and then 16 divided by 19, and then 19 divided by 22. All right, now the trickier part here is going to be actually finding the sequence that gives us this. Since we already know that 1/4 is going to be our u1, let's go ahead and write that down right here. Un is going to be equal to 1 divided by 4. And now let's just make this bigger. Since we know something's happening to our denominator and numerator, which is a plus 3, we can write plus 3, 3, just like that. But we're not done yet. We need to actually make this make sense by writing standard difference here. And if you recognize this, look at that. There's our d and there's our n minus 1. Simple, just like that, but this time we're just merging them into the fractions. And that gets us our solution, which if you plug it n equals 1, n equals 2, you get this little sequence over here. So yeah, that's that. Now let's go on to 1e. Let me scoot over to the left a bit. 1e states this sequence 1/2, 1/12, 1/30th, and 1/56. So we know that our numerator isn't changing. It's just going to stay 1. So let's just focus completely on our denominator here. Now, whenever I first look at this, there's no, clear visible pattern. Sometimes we have to just look outside the box. Let's write these numbers as multiplicities. So you have 1 times 2, then we have 3 times 4. Look at that, we're getting somewhere now. Let's continue. We have 5 times 6, and then 7 times 8. So this is definitely, a harder pattern to see. More than likely, you won't receive this on any actual IB exam. It's just confusing. There's probably some other way to do it too, but clearly there's a sequence here. We're just multiplying um, each term, leading up 1 times 2, then 3 times 4. So we know the next three terms are going to end up being 9 times 10, 1 divided by 11 times 12, and then 1 divided by 13 times 14. And then when we simplify this, it gets 1 over 90. Let's see, 1 over 132, and then 1 over, I think that's 182. Yep, okay. Scroll down a bit. But we're not done yet. We got these three terms. Now we need to create a general sequence. So un is going to be equal to 1, since we know our numerator is going to stay the same. Now this is the more tricky part here, actually finding the term that's going to go along with this. So let's scroll back up. Let's see something similar here. When we have numbers like 1 times 2, we can just split that up like that. So it's 1 times 2, but they're in brackets, so they're separate. So that makes it easier. Same over here, 3 times 4 like that, 5 times 6. So let's just start with the first bracket. We know that it's just going up by 2 every time, because look right here, plus 2, plus 2. And there's an easy sequence that gives that, which is just 2n minus 1. And since all of these are just multiplicities of 2, you can just write that as 2n. And there is our solution to 1e. Now let's scroll. Next up is 2. Just get all that out the way. Okay, 2a. For this one, we're going to have to take the first 5 terms of each of the sequences. So we're already given the sequence. Now we just need to solve them. So 2a gives us the sequence UR. So we're switching over to R. Just remember UR, UN. Same thing in this case. 3 minus 2R. And now, when it says the first 5 terms, they mean whole numbers. So we have R equals 1, 2, 3, 4, and 5. And I'm not going to show them each individually, but after plugging them in, you get 1, -1, -3, -5, and -7. Notice how it's going down by 2 each time, starting from 3. Well, next is 2b. This one gets a bit more trickier with fractions, but do not get scared. Remember, it's just simple math. Plug in r equals 1, r equals 2, and so on and so forth. And this should get you 1 divided by 3, 2 divided by 5, 3 over 7, 4 over 9, and 5 over 11. Simple math. It's going down to 2c. I'm like trying to get used to it's not like breaking every time I hold down on it. Right. Given UR is equal to 2R plus parentheses -1 R times R. This is a bit more confusing, but remember, it's all just going to end up being simple math here. We can end up simplifying this term into R because we can take the R out times 2 plus parentheses -1 R and then another parentheses. So this doesn't really solve it yet, but it does make it a bit simpler to look at. So now we just need to plug in 1 through 5 here. And after doing the math, you end up getting terms 1 and then 6, 3, 12, 5. All right, just like that. 2D. 2D states that UR is going to be equal to -1 power of R times 2. And this one's a bit more simpler than the other one. Simple math, and we just get -2, 2, -2, 2, -2. Since we're not adding anything, they're all just multiplicities of 2. Simple pattern. This pattern goes on forever if r goes to infinity. Okay, next equation is going to be 2e. Here we have UR is equal to 3 divided by 2 to the R minus 1, so that R is being subtracted. And after plugging in, 1 through 5, we get the terms 3, 3 over 2, 3 over 4, 3 over 8, and 3 over 16. Our numerator stays the same every time because, nothing is happening to this. And that's going to be all for exercise 2. Scroll down and start a new page at 3a. 3a is asking us to write each sequence using the general term u to the n. So it gives us the sequence. You have 5, 10, 15, 20. Simple arithmetic math. Our difference is going to be plus 5 each time. Our u1 coefficient is just 5. So then we get un is equal to 5 plus 5 and minus 1. The funny thing is, with this basically, this ends up just simplifying to 5 plus 5n minus 5, which is just equal to 5n. Just like that. Okay. Next is going to be 3b. We have 6, 14, 22, 30, so on and so forth. Okay. You can recognize that our u1 is going to be 6, and our difference here is going to be 8, plus 8 every time. So then we get un is going to be equal to 6 plus 8 and minus 1. And here, let's just continue and simplify it even further. We get 6 plus 8n minus 8. And that gives us un is equal to 8n minus 2. So both of these ways are correct. They're just two different ways to actually write them. 3c, given the sequence 1/2, 1/4, 1/8, and 1/16. Yeah, that's a comma right there, not a 1. But here, these are all just raised to the power of 2n. As you can see, 2 cubed is 8, 2 to the 4th, 16th. So simple, un is equal to 1 divided by 2 to the n. Is that C? Yep. Oops. Okay. 3d. We have 1, 1/3, 1/9, and 1/27. All right, recognize that this sequence is decreasing. So we're going to have our 1 on top here, and that's not going to change whatsoever. And this is being divided by, at first, 1. So we know our n equals 1 has to be equal to 1 here. And we notice that these are all, powers of 3. So easily we can already write that 3n. And then, as we said earlier, since our first term is 1, and any number except for 0 to the power of 0 is equal to 1, we can add a minus 1 right here. And when n equals 1, we get 1, and so on and so forth. This video was going to be a bit rough because, first time recording and everything. I'll get better with videos to come. Let's just continue. This is actually new. This time we're starting with 0, and we're increasing in intervals. So keep that in mind. At first, there's a very obvious pattern. We're going +3, +5, and then +7. Pattern here isn't too obvious, but what we can notice is that these are all odd numbers. And an equation that gives us odd numbers. We have 2 here. We have 2n minus 1. We also have n squared minus 1. So let's look through both of these. When we plug in 1 into this equation right here, we get 2, 1 minus 1, and that's going to end up equaling 1. But our first term is 0, so this does not work. Onto the second equation, if we plug in 1 here, we get 1 squared minus 1. That equals 0. Well, that works. But if we continue, 2 squared minus 1, that equals 3. So yeah, you can assume that the next is going to be correct since it's just increasing by odds, and n squared minus 1 gives you odds. So you can write down un is going to be equal to n squared minus 1, just like that. Okay, number 4 introduces us to sigmas. Remember, sigmas are basically just series, but real notation. There's a summation of a couple of terms. 4a is giving us the summation from r equals 1 to 4 of 2r 1 minus r. And unfortunately, there's no easy way to do this except for just plugging in r equals 1 and then adding that to r equals 2. So by doing this, we have 2, 1, 1 minus 1 plus 2, 2, 1 minus 2, and so on. This ends up getting us 0, minus 4, minus 12, minus 24. And just to recollect, remember this is r equals 1, r equals 2, r equals 3, and r equals 4. I just didn't write r equals 3 and 4 because space-wise, and I just don't want to be reductive. It's not actually asking us to solve, it's just asking us to write the series. So we can leave it like this, and that is the answer. The real answer would be like negative 40, right? Yep. But yeah, not asking us to do that, so don't go over yourself. 4b, we have the summation from r equals 0 this time, and till 5. It gives us this series of negative 1 to the power of r to r or times r squared. So some will actually write it out a bit. So we'll have negative 1, 0, 0 squared plus negative 1, 1, negative, oh, 1 squared plus negative 1, 2, 2 squared, and so on. And then this gets us the series 0 minus 1 plus 4 minus 9 plus 16 and minus 25. Notice that these are all perfect squared numbers. The reason being is that r squared is a perfect, square number of integers. All we're doing is adding this, which is going to switch it from positive to negative, positive to negative. All right, 4c. Going on, we have sigma r equals 1, 5 of the series r divided by 3r minus 1. And doing what we were doing earlier, just plug in r equals 1 and then add that to r equals 2, so on and so forth. And that gets us 1/2 plus 2/5 plus 3/8 plus 4/11. And our final term, 5/14. Okay, 4d. Sigma r equals 1, 4, and the series it gives us here is just 5. Notice how there's no r variable. I mean, we literally cannot plug r into this, so it's just going to end up being 5 plus 5 times r, but look at that, we have no r. So 5, 5, 5, which is just 20. Easy peasy, just like that. Okay, the last one for 4, we have sigma 3 r equals 0, r squared minus 3. All right, those parentheses don't have to be there, but it does give us in parentheses, so I'm just going to write it down. Once again, same thing we've been doing for each of these. Just plug in r equals 0, and then r equals 1, 2, and 3. So we'll have 4 terms. I have -3, 3 minus 2 plus 1 plus 6. Just like that. All right, let's go on to 5. 5 asks us for each of these sigmas, we need to write the first 5 terms. So basically what we were doing earlier. However, it tricks us up a bit. We get the sigma from r equals 1 to infinity. But as I was saying, don't get scared here. This infinity means nothing to us right now because we're only finding the first 5 terms. So writing this down, we're just going to do what we were doing earlier, plug R1 through 5, and we get a simple little sequence here. Now, remember for this, it's asking us to just write the first 5 terms. If you were to do, plus for each of these, you'd end up being wrong because it's asking us to find the summation. Oh, as I say that, I write plus. But again, yeah, it's not asking us to find the summation. It's just asking us to write the first 5 terms. Simple as that. 5b, sigma infinity, r equals 1, equals 1 to the r divided by 2r squared to the minus 1. And then I won't do all the math, but these are the terms. Double check yourself and everything. I'm running out of space. Gotta write a bit smaller, I tell you. 5c. Now we're straying away from the infinities. Sigma from r equals 1 to 20 of r parentheses 5r minus 1. Don't forget about the r on the outside. And simple math gets us 4, 18, 42, 76, and 120. I noticed that these videos are starting to get a bit long for just one exercise, but should be fine. Try to go quicker in the next ones. I wonder how those word problems are going to end up actually doing to me. Okay, once again, this time we're taking from the r equals 0 through 5. And that gets us -2, 1, 1, 5, 13. And then I actually forgot to write the fifth term down. What would that be? To the r, 32 minus 3, 29. Okay, 5e. Sigma infinity, r equals 1. Notice how they switch from r equals 0 to r equals 1 here. 0 to the 0, still undefined as we know in math. But after taking the first 5 terms, 1, 4, 27, 256, and 3,125, huge exponential increase. Okay, looks like we're getting to the last part of the exercise. And for number 6, they just want us to write each of the finite sums in sigma notation. So they give us a series here. 8, 5, plus 2, minus 1, minus 4. And these are the first 5 terms. We can recognize that the arithmetic sequence for each of these is going to be minus 3, minus 3. So we know our d is going to be equal to negative 3. Let's go ahead and write the sigma. Since we know it's the first 5 terms, we can write a 5 right here, and we can write n equals 1. So let's start how we usually would. We know our u1 is 8. Let's put that on there. And it's getting plussed by, oh, well, I shouldn't say plus. I should say subtracted from 3, since that's our difference, with n minus 1. And when we end up simplifying this, we end up getting sigma 5 n equals 1, 11 minus 3n. Next, 6b. We have 3 plus 10 plus 21, 6, 55. So the amount of terms in here, 1, 2, 3, 4, 5, 5 terms. So let's go ahead and write the sigma with 5 n equals 1. Off the bat, there's no instantaneous common or difference I see here. So let's just check. We have 1 times 3. 10 is going to be equal to 2 times 5. 21 is going to be equal to 3 times 7. You see, I'm starting to see a pattern here. 4 times 9. 5 times 11. Okay, so we spotted a pattern here. These multiplicities, first multiple is getting increased by 1, while the second one are just all odd numbers that aren't 1. And this is kind of what we were doing earlier. So let's write that down. Since n is just going to be an integer for each of the first multiplicities, you can write that. And since the second multiplicity for all of these is an odd number, you can write it as 2n plus 1, not minus 1 this time, because our first one is 3. And that gets us our solution. Okay, 6c. Here we start with 0, 1/3, 1 over 2. So next, 3 over 5. 2, oops, 2 over 3, 5 over 7. Okay. At first, there's no like real pattern going on here. We know that there's going to be 6 terms in the summation. And since our numerator is actually going to start off as 0, since our denominator can never be 0, we know that n is going to have to equal 1 for this to work and not 0, because if our numerator or denominator is 0, it's just not going to work. So we have n minus 1 on top. At first, when I was looking at this, I didn't really see a pattern. It is a bit confusing, but then I realized you can end up actually making these fractions into what is unsimplified terms. So we have 1 over 3 here, and then 1/2 is just 2 over 4. 3/5, 3 over 5, and 2/3, what's that, but 4 over 6, and 5 over 7. Now we can see the easier, what is it called, sequence going on here. It's just plus 1 each time on the denominator, and that gets us this. Boom. I'll admit that took me a second to figure out, but we have it now. Going on to 5D. 1 plus 9 plus 25 plus 49 and 81. Okay, first thing I see is these are all perfect squares, but none of these are even squares. I know these are all odd squares, 1 squared, 3 squared, 5 squared, and whatnot. And after counting the terms, 1, 2, 3, 4, 5, and n equals 1. Remember our, oh, what's that? That's not good. Okay. Well, ignoring that, since we know our equation for odd numbers is going to be 2n minus 1 in this case, since we do start with 1 squared, that is our solution. Next, 5e. Hopefully it doesn't like kick me out as I'm writing this. All right, 5e. We actually have k's this time. We have 3k plus 6k, 9k, 12, and 15k. All right, our constant factor here is k. Don't get scared by this. We're just going to introduce a new variable into this. But as you can see, it's increasing by 3k each time. So, it's going to be a simple arithmetic with 1, 2, 3, 4, 5 terms from n equals 1, 3k times n. Just like that. And, oh wait, did I accidentally make that 5? Sorry about that. This is 6. That's also 6. But that is going to be the end of this exercise. Hopefully you either got your question answered, helped a bit, and I hope this can help any future generations. And that's going to be all for today. Thank you for tuning in.